So we left off with page 14. We set up our ice table using the NO concentration at equilibrium that was given in the problem and the initial concentration along with the stoichiometry. We were able to find all of the equilibrium concentrations. So we used this equation to solve for x and then plugged it in for x. And that's how we found those final concentrations. Then I wrote the K expression, and then we will plug it in.
Professor, does it matter if the values are in the correct order? And by that I mean for like the numerator, you have H2O squared N2, and I have it the other way. Does that make a difference?
No, it doesn't, because it's all multiplication, so the order doesn't matter. And then I got 653. All right. Okay, so does that lie towards reactants or products?
Product.
Yeah, it's a bit more products.
Mm-hmm.
It's somewhat balanced. It's not hugely out of balance. Everything's present at once, but there's more products because it's a large value. Okay, let's do another one. All right, so at equilibrium, and then the total pressure So we have a sample of just the SO2Cl2. So this is going to start with zeros there, and we don't know how much is here. But we do know how it reacts, right? The change during the reaction, some of this is going to go away, and that same amount will be produced for each of these. So at equilibrium, you'll have X atmospheres of SO2 and X atmospheres of chlorine. So the total pressure is going to be the sum of these guys. What we're looking for is the Kp. Okay, so if you're given the K value, then you'll need to write that equilibrium expression, set up your ice table underneath the chemical equation, and then figure out what those changes are in terms of X. We might need to use the law of partial pressures to find the equilibrium pressures, like we just did. Then we're going to find that X, calculate our concentrations at equilibrium, and plug them into the K expression. So this one's looking for Kp, and we have the hint to use the gas law to get our initial pressure of SO3, right? Because it starts with a mass. From there we can get the N, a V, and a T, and then we have that total pressure again. All right, so that is P equals nRT over V. So I'll put the 1 liter down there if that's cool. And then where I had N, I plugged in mass over the molar mass. So starting just with that reactant, so these both start with 0. All right, we've got a total pressure. Right, and this is at equilibrium. SO2. Okay, so plugging in that X, we get our concentrations of each species in the reaction. And then we're going to calculate our Kp. All right, then to get to Kc, yeah, I always forget that formula, so I like to derive it.
Products minus reactants.
Yeah, it should be
Oh,
1.
okay, that's what I did wrong.
Yeah, I just found a different mistake in my work, but I think I calculated it correctly. Right, there's an extra pressure on the top, right? There's 3 factors of pressure in the numerator and 2 in the bottom. So we're going to have to take 1 pressure and convert it to, in gas law terms, an N over V. So that means that we're going to, looking at this where we have our RT factor, I'm going to divide out that RT. So I think this means that Kc is Kp over RT in this case. So for those of you who use the formula and rearrange it, is that what you got?
Because the power was 1, so it's over just
Oh,
RT.
that's right. That's right.
Yeah, that checks out then.
Excellent.
Do we give in the formula sheet, is it given or got to memorize it?
I will give it to you.
No problem. Thank you.
I mean, we did one of these already, and I messed it up using the formula. I don't know if you remember. So it's like I just want to derive it each time because then I see it and I feel more confident. But I'll give you the formula. All right, so we need our RT factor.
And the answer should be unitless, right?
Yeah, and that's why I dropped the units on there.
Shouldn't we be using the R value in atmospheres? Is that the R value?
Yeah, that's liter atmospheres per mole Kelvin.
I thought that one was the joules. I must be misremembering. Sorry about that.
Yeah, joules are 8.314.
Okay. All those eights.
And we'll get to those. Yeah, we'll get to the joules pretty soon. All right, now we get a 28% dissociation. Let's see. Oh, and we're looking at the Kc, and we've got a volume that's not 1 liter and a moles. So we'll calculate a molarity for that. Then the amount that dissociates, which I believe because of the molar ratios is going to be this one. It's going to be 1.66 times 0.28. So I always have this question, do they mean the x or do they mean the 2x? But I think that usually when they talk about a percent dissociation, we're talking about the initial concentration being reduced. 28% reacts forward. So let me set up my ice table. So initially, 1.66 molar, 0 and 0. Then there's some change that happens and we get to equilibrium. At equilibrium, we have 0.466 molar. That equals 28% of the original reactant.
Wait, so the initial starting value for nitrosyl chloride isn't 2.5?
Well, that was the moles. So we'll be looking at a molarity. So the first thing I did was divide by that volume to get into a molarity. So in this case, that percent dissociation gives us a way to get those equilibrium values.
Oh, so earlier you said you don't know if the 28% is for 2x or x. How do you determine that?
I think that I'm not sure. I think it's going to be the 2x. So I was just looking to see if I had any notes on why that is and where that definition is made. When we talk about percent dissociation, we'll talk a lot more about it with acids and bases. That's just another way to say how acidic something is. 100% dissociation is very clear. So let's just work with it like this.
Oh, so from 0.466, and then you divide it by 2 to find x, right?
Yep.
Just skip one step.
So we use this part right here as its own little equation to solve for x. All right, I get 0.0351. All right, so this one's going backwards. All right, so we'll use that ICE table. What happens during the change? And then we're going to plug this in to that value. Quantity squared. Oh, you know why? How can we solve this? Have you guys figured it out?
Quadratic equation. Multiply 2.4 times 10 to the 3 by the denominator, and then just try to solve for x squared.
Yeah, so that would work. There's actually a quick and easy trick for this one. We don't have to do the quadratic. The quadratic equation is time consuming and kind of a pain. And that's introduced on page 19. I swear I thought I saw it in these notes. So it is, we are going to have to use it. It's on page 19. But we don't need it yet because, anybody see this little math trick we can use? Take the square root of both sides. So square root of 2.4 times 10 to the 3 equals x squared over, just x, over 0.2 minus 2x. There we go. Then we can just plug it in and solve for x. All right, I'm going to call that 49. All right, so then we'll go back in and fill in our table with those equilibrium concentrations. Initial change, equilibrium, and then these are our final concentrations. All right, so in the next section, we can take a look at the same expression. We can evaluate that equilibrium expression for non-equilibrium conditions and compare the value to the value of K. So we know that K is the constant when it's at equilibrium. If it's not at equilibrium, we're going to call it a Q because it's just the quotient. So Q is like K, but it's not at equilibrium. So we'll put in the initial concentrations or whatever concentrations we're given, calculate a value for Q, and we can compare it to K. If Q is smaller than K, which direction does it have to go to proceed towards equilibrium? If Q is less than K, then that means it needs more products. That means that the numerator is small, right? So the reaction has to go towards products to reach equilibrium. If Q is greater than K, that means there's too many products. That means the numerator is too big. So the reaction is going to proceed back towards reactants to get Q to equal K.
So if Q is less than K, it's still going forward or tending to go forward, and if it's greater than K, it's going back.
Yeah, that's right.
Okay.
And you can see that algebraically by the value of K, by the expression of K. If Q equals K, then we're at equilibrium. All right, so there's all these graphical ways of looking at it. I'll leave those to you to interpret. Oh, so we're just going to use the same technique of building that K expression, except it's going to be a Q now because we don't know if it's at equilibrium. So that is the reaction quotient. Okay, I just wrote them all in concentrations, but we'll plug them in as pressures. So let's make this a P. Okay, is it at equilibrium? Nope. So which way is it going to go? No. So the Kp is 1.05. It's less, so then it's going to proceed towards products, right? Okay, here's another one. So we're given a Kp. So we're given moles and liters. Have you calculated your Kps yet? You have to get a pressure from those.
Wait, is that KP or KC?
I'm building a Kp from the information given. So I was kind of waiting to make that connection between writing the expression rather than just popping in numbers and comparing. We have to write that K expression over here and recognize those have to be pressures. So we're given an N and a V and a T. So I'm just building the pressures right inside that formula because it's pretty easy. It's not too many factors, right? There's our molarity, then we have our R and our 298 Kelvin. And then this whole thing on the bottom is squared. Is that clear? Awesome. All right. Yeah, so I lined them up with the inequality sign, so QP was less than KP. So we need that numerator to be bigger. And then what is next? The quadratic formula. And there's a couple of things when we get two answers out, we'll need to look at those answers and see if they're reasonable. And so one thing that could happen is if you had like a starting point 200 molar and you got an answer that was larger than that, so you're solving for x, x can't be larger than that, so you would throw that solution out. And we're not going to have negative pressures, right? So you would throw that one out. So you have to look at the answers and decide what is physically reasonable. So this one, it looks like we are going to have a quadratic. We'll have a couple of those.
What was the answer for the last one? I was still working through it when you went.
I got 2.494 for Q.
Okay, thank you. That's close to what I got.
Okay, cool. Have a good weekend, everyone. Don't forget to come back to the quiz.
I just had a quick question. As we write up the lab report for like the method portion, write it as if we were doing the experiment, or should we just say we followed the instructions on the lab manual kind of thing?
For the formal, go ahead and write it as if you did it, but you don't have to do like a step-by-step procedure. It's more of a higher level method. Like you would still give the reactants and the conditions and explain what happened. And specifically with what reagents are used for the catalyst, for example, but you wouldn't have to say, and then I took 10 milliliters and added 20, like not a step-by-step procedure, but a higher level method of what was the approach.
Got it. Yeah, I think that's what the formal lab report sheet that you put on WAMAC was saying.
Yeah.
So that's what we're turning in, right? Just the formal lab report.
So yeah, what are the basic measurements you're making? What causes color changes? How are you calculating that rate? Like what's the thing that you're calculating? So you might say, we are going to change the concentrations, and then we're going to do the temperature study, and then we're going to add the catalyst. So that kind of information, what caused the color change?